Hello, my name is Scott Bryson, and I am an applications engineer for Texas Instruments' current and position sensing product line. In this video, we will introduce you to three-dimensional Hall effect sensors and explore a few cases where they help expand position detection capabilities and help solve system-level challenges. Hall effect sensors are useful devices for tracking and monitoring the position of a magnet. Typically, these devices are offered with switched, latched, or linear outputs. Each type of device utilizes a Hall element, which is used to measure an applied magnetic field. The Hall element is excited by a current. Under normal conditions, the charge density through the conductor will disperse evenly. However, if we apply a magnetic field orthogonal to the element, then the applied field causes the electrons to crowd toward one side due to the Lorentz force. The unequal charge distribution creates an electric potential perpendicular to the current which we can measure. This small voltage can be gained up and then used as an effective method to measure the field strength normal to the surface of the Hall element. The nature of the Hall effect is inherently one-dimensional and can be quite useful in various mechanical arrangements. As long as we take care to properly align the magnet and sensor, we can achieve position tracking anywhere within range of the selected magnet. In this simple head-on configuration, we see the magnetic flux density produced by the magnet decays with respect to the square of the distance from the magnet. This might be used to define the end of travel based on a predetermined output threshold. While there are many arrangements of magnet and sensor that are achievable, we should acknowledge that the nature of the magnetic field is not one-directional, and it can sometimes be difficult to achieve perfect alignment in every system. When we trace out a sample of the field lines produced by a magnet, we observe that the field is complex and that there is more information than could be detected by a single Hall element. Following a single field line helps to visualize the change of the direction of the field vector. As we travel around the magnet, we see the direction of the field vector is constantly changing. Depending on the motion of our magnet, this can result with various measurement challenges. Let's suppose that our magnet cannot be aligned properly. If we offset the sensor from the head-on approach so that it is no longer aligned to the pole of the magnet, we will observe at larger distances that the measured magnetic field is very similar to what was measured before. Also, the magnetic flux density appears to rise at about the same rate at first. Then, as the magnet continues to approach, the flux density begins to change direction, and the output drops to zero. To complicate matters, after the input field peaks, we can no longer determine which direction the magnet is moving. In a real application, this may result in the mechanism damaging itself due to uncertainty of position. Some configurations take advantage of the changing direction of the magnetic field vector. During this lateral sweep, we can detect the field in the z direction and observe an interesting output behavior. In this particular case, we have a very linear input region that corresponds to the length of the magnet. The zero crossing occurs with the magnet perfectly centered above the sensor. While it is very easy to determine position in the linear region where the magnet is above the sensor, one-dimensional visibility restricts the measurement range. Any travel outside the linear region will require additional sensors, since each output level could now correspond to two locations. Other applications may use two sensors carefully placed for matching inputs produced by a rotating magnet. This function requires two sensors 90 degrees separated, and is an excellent way to monitor angle. Misalignments and other factors such as sensitivity mismatch can produce measurement errors which will affect system performance. Here we observe that the magnitude and alignment errors will impact the ideal 90-degree phase shift between the outputs, which will ultimately define system accuracy. If we were to integrate three mutually orthogonal Hall elements into a single package, we can limit variation between sensors and maintain a fixed 90-degree mechanical separation while also allowing one device to detect all three components of the magnetic field. In the case of the rotating magnet shown here, the X and Y field components naturally maintain an ideal 90-degree separation. For devices which also integrate field vector normalization, the sensor can be placed virtually anywhere the field may be practically measured, making them widely adaptable to their mechanical environment. Examining the device more closely, we see that the new sensor will have three separate Hall elements integrated into a single package, one for the Z component as before, one for the X component, and one for the Y component. Independently, each sensor is only sensitive to a single component of the B field vector. When used together, however, we are now able to detect the complete magnetic flux density at our sensor location. When we revisit the linear sweep, we find that the X component provides more insight relative to the location of our magnet. With an expanded view of the vector, we can use the X component to define operating zones. If the X component is below the specified threshold, we know that the magnet is in the linear output region, and when the X component is above our threshold, we can now distinguish the approach or removal of the magnet from either direction based on sign and magnitude. Finally, returning to the head-on alignment with offset, we now observe all three field components. Taking each into consideration, we can calculate the magnitude of the field vector and obtain a response which is similar in behavior, although lower in magnitude to the scenario with the sensor perfectly aligned to the pole of the magnet. In effect, we achieve greater design flexibility while being more forgiving for mechanical tolerances. This enables precision motion detection even in unusual circumstances. Three-dimensional Hall effect sensors can help simplify your design requirements and provide greater visibility to the surrounding environment. If you would like to learn more about our Hall effect sensor portfolio, please visit www.ti.com/Hall effect to explore our technical resources and products.